I'll be back.
Get the warhead, and we hold the world ransom for $1 million.
Do you expect me to talk?
No, Mr. Bond, I expect you to die.
It's over, Anakin! I have the high ground!
Hello, students. I'm Ross.
I'm Gilbert.
And we're back to bring you another intro video to a project. This time, you're coding up Lines of Action, which is another game. So hopefully you guys have taken a look at Lab 9 already, which walks you through how to grab the project from the shared repo, how to run the staff version of the project and hopefully get familiar with the game a bit, and also how to write some tests, some integration tests for the project. So if you haven't yet, I recommend you take a look at this and work through Lab 9 so that this video will help you as much as possible. We'll pretty much be covering everything that has to do with the project, starting with the rules. So let's begin.
Let's get started.
All right. So here is the game Lines of Action. So there's two teams, black and white, and I think I'm black in this case. Yeah. So on every turn, you can move any piece as many squares in one direction as there are pieces on the board in that direction. And you can either move diagonally, vertically, or horizontally. So in this example, in the vertical direction, there are two black pieces, and so you're able to move 2 squares forward if you want.
So one thing to keep in mind is that you have to move exactly the number of spaces that there are pieces on that line. So in this case, you can't move just one line or one space. You have to move actually 2 spaces.
Won't let me move 1 space, but I can go ahead and move 2 spaces. All right. So if you happen to land on an opponent square, then you can just go ahead and capture the opponent. So in this case, I can capture that white piece there.
Cool. So let's see if we can actually demonstrate a case when we actually can jump our own piece.
Oh, yes. So can I jump my own piece? No, not really. Oh, yes, I can. So on this line, there's 3 pieces, so I can move 3 squares forward. And you'll see that I'm allowed to jump over my own black piece here. Now, interestingly, you cannot move over your opponent's pieces. Do I have a good example of that? Yes. So check this out. So there are 3 pieces on this diagonal here, and so I should be able to move 1, 2, 3 spaces, but I can't because this white piece is blocking. So in short, you can always jump over your own pieces, but you cannot jump over opponent pieces.
The one thing to keep in mind though is that to capture, you can jump exactly onto your opponent's piece.
Oh, yes.
So it's a small distinction you have to make, but it's pretty important.
Yeah, so capturing, you land on the opponent, and you can never jump over them, right? So now let's talk about the win condition for the game. So you win Lines of Action when all of your pieces are connected together, either vertically, horizontally, diagonally, in one giant blob, basically. And there's a picture in the spec that illustrates that right here. So if we take a look at Black's pieces, you'll see that they're all connected to each other. Essentially, you can reach all of Black's pieces from starting at a single piece and then just either moving in any direction and landing on a piece each time. And
so all of Black's pieces are just adjacent to each other.
Yep. And in this example, white is not winning because these 2 pieces are not connected to the rest of white pieces. And this is also separate.
So there's one special case that we do have to consider. So if we take a look at the second situation over here, if white moves to capture black, you'll notice that both white and black will have contiguous pieces. However, because white made the move to create that end situation, white will be the winner. So there are actually no ties in this version of our game.
Yep, no ties. So the moving player always wins if you would otherwise create a tie. All right, so I assume at this point you've had the chance to look at the spec and played around a little with the staff version of the project. And now you're ready to really get into the thick of things and start reading the code and start writing some code. So this is going to be phase 1 of the project, which is the logic for the board itself. Now, you shouldn't worry about the command line for the project yet. The first thing you should do when you're doing this project is focus on the actual board logic and build from there. So, as is customary with Hillfinger projects, there is a lot of code here already. So it'll take you some time to really let it sink in, figure out what's going on. A lot of it has been written for you, and a lot of it is still left to implement. And I'll be talking over some of the more interesting parts of the board. So let's start with maybe the most basic commands here, which are set and get. So get just returns the contents of column C at row R, which are indexed from 1 to 8. So first thing I want to do is make an important point here. So in the staff version of the project, you'll see that the board is labeled with rows from 1 to 8 and columns from A to H. Now in our standard indexing in the project, the columns are going to be indexed from 1 to 8 as well. So where you see an A, you should see a 1, and so on. So this square would actually be 1, 1 in the board. So calling the function get will return you whatever piece is at that spot. Now, what is a piece? Well, a piece is just a class, or an enum here, that can take on only 3 values, either a black piece, a white piece, or an empty. And so calling get will return that, and calling set will put a piece there. Now, right off the bat here, in order to even write these functions, you're going to have to make a very important decision, which is how you actually want to implement your board and what data structure you want to use. The board is an 8x8 board, so perhaps you want to use, say, a one-dimensional array to keep track of things, or a two-dimensional array, or an array list of array lists, or some other kind of data structure. It's up to you, but that's the first thing that you'll have to decide before you can write these functions. So after you've written those, then we can actually go ahead and, well, initialize the board when we start a new game. So there's a function initialize, which loops over the board and indexes some array of contents, and then sets those places in the board. So what is contents? Well, initially, contents is going to be this initial pieces array, which is a two-dimensional array. And this just contains the initial setup for the board with empty pieces in the corners and all the middles, black pieces on top and bottom, and then white pieces on the side. Now, another important note about indexing here. So these for loops run from 1 to 8 here. And since we do r minus 1, this will start at contents of 0, 0. So I'll be grabbing from this spot here, this empty, then this, and this is how we're looping through initial pieces. But when you call, say, set with those indices, as is happening here, the first thing you'll do is call set of 1, 1. So 1, 1 corresponds to this square down here. So in initial pieces, this top left square here is really what's going in the bottom left. So this whole thing is kind of flipped initially. That might not really matter for your initializing, but just always keep in mind that the indexing is done this way, and keep it consistent throughout your code. So that is the initial setup for the board. Let's talk about other stuff. So now here's some functions: make move, retract, and is legal move. So these guys work with move objects. What is a move? Well, move is this class which contains a whole lot of static methods that return moves, and then this big static block down here I'm not going to get into the super details of this, but essentially all of these functions just return a move. So if you call move.create with some parameters, it's going to give you a move object back with those parameters. Now, move object just represents a single move in the board, and it contains, I believe, 6 pieces of information. It knows the column and row of your source, the column and row of your destination, so where you're moving a piece to, what the piece is that got moved, and then what the piece is at the destination. So if you capture a piece, that would be the replaced piece. So make move, well, you can call this function in order to actually make a move happen in your board, and retract will undo a move. This is very similar to the undo feature in Project Zero, but you don't have a command in the project which is undo, so you're probably wondering what the point of the retract method is. Well, that will be useful to you when you implement your AI, because you'll be wanting to try out a lot of moves, but we'll talk about that later. So there is this function isLegalMove that you have to write, which checks whether or not a move is legal for the player currently on the move, or whose turn it is. So in order to write this function, you'll make use of these guys down here, which are piece countalong and blocked. So piece countalong tells you how many pieces are in the line of action indicated by move. As you know, you can only move exactly how many spaces as there are pieces in a line. And also, blocked will tell you whether or not there's an opponent piece in the way stopping you from making a move. So all of these will help you write your isLegal function and figure out whether a move is actually possible before making it. And then there is this game over function, which checks whether or not a player has actually won the game. And that just calls this function pieces contiguous with either a black piece or a white piece. And so what that's asking is whether or not one side's pieces are all connected together in one blob. Now, this function, you will probably find this one of the trickier functions to write throughout the project. My recommendation to you is please use a helper method. A helper method will make your life much, much easier. Don't just stick with this piece contiguous, because there are better ways to do this if you keep track of more information. And helper function will do you a lot of good. And I think that's all I want to talk about now for the board class. There's a lot of other functions and classes, but you will find them more useful in later stages of the project. I do want to make a note about testing, though. So while you are writing the board class, you should be testing all the time. Please test your code. I recommend that you don't worry about the command line yet. So when you test board, use JUnit tests. In fact, I want you to pause this video right now and open up a new file and call it, boardtest.java or something, and start writing tests as you are filling out the board class. Please do this. If you don't, I will call the local newspaper and tell them how you fell on the playground when you were little. Testing will make your life much, much easier. So I highly recommend it. And yeah, that's the board class.
Hey everyone, Gilbert here, and today I'm going to be talking about the piece, direction, and move classes for our lines of action project. Let's start with looking at piece and direction, but before we go into any detail, let's figure out what an enum is. So in Java, an enum is an easy way to define a set of constants. Examples of this could be something like days of the week or planets, for example. For our purposes, we're going to be using them to describe different piece types and different directions. So notice in piece we have BP, WP, and EMP, and these represent the constant names that we'll be using to represent black pieces, white pieces, and empty pieces or empty spaces. Same goes for direction. We use the nowhere constant to describe going nowhere, and we have different compass directions to describe going in those directions. So just like with classes, we can declare additional methods, but what makes enums a little bit more useful is that we have access to a few methods, and the ones that you'll be seeing in the project and that you might be using yourself are going to be the values method, which is a static method, and the ordinal method. So what the values method does here is it's going to return an array containing all of the constants that we've declared in this order. So in other words, it's going to return an array of length 3 with BP at index 0, WP at index 1, and EMP at index 2. What the ordinal method is going to do, it gives us the index of this constant in that values array. So in this case, ordinal on BP is going to give us 0, on WP is going to give us 1, and on EMP is going to give us 2. So let's see that in action, and what I've done is I've created a very brief main method. All it does is it iterates piece by piece, prints out the piece's ordinal method, and calls one of the piece methods. In this case, I decided to call full name. What I've also done is you can actually access different constants, enum constants individually, and the way you do that is you'd provide the enum name and then the specific enum constant. So in this case, piece.bp is going to give us the BP constant, so the black piece constant. We can also call methods on these constants, like so. So piece.wp.abbreviation will give us the white piece, and on that white piece we call the abbreviation method. So let's see this in action real quick. Go ahead and compile, and let's go. Great, so notice how the first loop does exactly what we thought it should. So in other words, it prints out the enums in the order we declared them. So in this case, BP, WP, EMP gave us the ordinal values, basically the array index, and then gave us the right method call. For the lines below, notice how when we printed out BP, it gave us that string BP, and the line below it, we called piece.wp.abbreviation, and that correctly gave us the abbreviation for a white piece. Cool. So the direction class is going to be relatively similar, except we have this weird sort of parentheses notation. It looks a little intimidating, but all it is that when we create these enums initially, we use this constructor, and in our constructor we have these two instance variables, DC and DR, and these represent steps in a certain direction. So if DC is positive, that represents a step to the right one, and if it's negative, it's going to represent a step to the left one. Very similar with row. If DR is positive, that represents a step upwards, and if DR is negative, that represents a step downwards. So hopefully at this point you can see that we can use a combination of these values to represent different directions on a board. So in this case, north is going to represent 0, so 0 steps to the left or right, and 1, so 1 step upwards, which is the north direction. All of these direction constants have a successor method, and all that's going to do is going to return the next direction clockwise. So if we have north, so notice how we use ordinal here to give us the next, ordinal plus 1 to give us the next step. In this case, north dot successor is going to give us northeast, northeast dot successor is going to give us east, so on and so forth. So just like before, I went ahead and access the directions array to print out every direction, and I printed out the direction, the ordinal value, and then the step that that direction represents. So let's go ahead and see that. Cool. So notice how we have, again, in the order that we declared them, the constant name the ordinal values, the index in the array of constants, and then the step that each constant represents. So up next is our move class, and we use the move class to represent different moves for our lines of action project. There are 3 different ways we can create moves. We can create moves given a string that matches the format given in the spec. We can create moves given start positions, column 0, row 0, and end positions, column 1, row 1. Or we can create moves given start positions, column 0, row 0, and a step of length k in some given direction dir. If any of the moves we try to create are invalid, the method should return null. And keep in mind that this is a static method, so the way that we'd call that would look something like this. It would be move.create, and then we'd pass in some different arguments here. Cool. So up next is our private constructor. And all this assert statement is saying is that, first, our move must be inbounds. So in other words, the start positions must be on the board, and the end positions must also be on the board. The next block here says that our move must be in a straight line. And the final block says that we have to be moving a black or white piece to an empty piece or to a different piece. Here we have different getters and setters to access different instance variables for our piece. And then down here we have our toString method, which should return the move in the format given in the spec. So in other words, we have the start position dash end position. Cool. So now we have this crazy 6-dimensional moves array. But let's break that down. The first array is the start column. The second array here is the start row. The next array is the end column. Here is the end row, so the fourth array is the end row. The fifth array is going to be the type of piece that we're moving, and the sixth array is the type of the piece at the destination. So that can be either black, white, or empty, and for the piece that we try to move, that can only be either black or white. So what happens here is that this is called a static block, and what happens in a static block is that when we load our project initially, so say when we call java.loa.main or java.loa.main and we start our project, this block of code will execute just once. And so what's happening in here is that we generate all of the possible moves that could happen in our game. So later on, when we try to create a move, you'll notice that all the create actually does is rather than create a new instance of a move, it looks within our moves array and just retrieves a move from our pre-constructed set of all possible moves. And that's it.
All right, welcome to phase 2 of the project, game.java and interpreting player commands. So at this point, I'll assume that you've written board and tested it well and are sure that your board implementation works. And now you're ready to move on and start actually processing commands from the user so that you can actually play a real game of lines of action, either against a real player or an AI. So this phase of the project is going to involve game.java mostly, because this is the class that's going to handle all the processing of inputs from the player. And also, you'll be making use of the player class, which is abstract. There's actually 2 types of players in this project, human and machine. Machine player we can worry about when you write your AI. So for now, mostly you should be looking at human player, which the human will type in commands to the terminal. So I'll be talking a little bit about how human player is supposed to work and also how game is supposed to work. So first thing is there's a lot of code going on in game.java as usual. So I would recommend trying to look for places where you might be able to just experiment and see if you can make new things happen. So for instance, I think process command is a good place to start. you might come across all of these cases in this switch statement, which looks like it's just looking for a command from the user and then figures out what to do with it. So what's going on here is process command takes in this line from the user, and then it's going to match that line against this regex pattern up here. And it uses that regex pattern to properly split the command into different parts. And so then we can analyze just what the command is, and then based on that, what its argument should be. So for this part, it will be useful to you to brush up on your regex skills and figure out what these groups are actually doing and then how you can use them. So I would try experimenting and see if we can actually get a command, see if we can add a command here, get it working. So let's take a look at the spec, see if there's any good command. How about dump? So dump is useful for testing and debugging. It gives you an 8x8 printout of the board, tells you who the next move is, and it has these equal signs that are very important for our autograder. So it's important to get this formatting right. So let's try adding a dump command. So you might add a case that says, I don't know, if the user types in dump, then maybe we want to print out some nice representation of the board. Hint, board has a toString method. So if we print out our board object here, then let's see if we actually added the command properly. I'll type dump. And there it is. There's our board. Cool. So process command, that's how you're going to add new commands from the user. And then, well, figure out what to do with them. I'll stop this. All right. So process command, well, it gets called from somewhere. So let's figure out what is actually doing the work of calling process command. Now, the most important function to actually making the game run is this play function here. Play gets called inside main when the project first starts up. It just creates a new game, and then it calls game.play. So game.play contains the main loop here, the while loop, that's just going to run as long as the game is actually running, and as long as you're actually playing. Oh, actually, I should make a distinction. So in this project, there is a difference between while the game is running and you're actually in the middle of a game versus the program is running but you're not actually currently playing a game. Like you can't, it's not anyone's particular turn to make a move. And so that is determined by this playing Boolean here, which is true if you're actually playing, like a game has started, which means it's someone's turn and that person needs to actually make a move. So as long as we're playing, what we're going to do is, well, see if the game is over. And if it's over, then we need to stop playing because someone won. If not, then we just get whoever's turn it is, and then we call the make move of that player. And that player needs to provide the function with, well, a move. That move will either come from the human terminal input, or it will come from an AI. So it depends on who this make move is actually being called on. So what happens is we have two types of players, a human player and a machine player. So if we call make move on a human player, we're going to come in here inside the human player class, and there is this make move function, which currently does nothing, but we need it to return a move that the user actually wants to make. So it says here, we create a human player that plays on the side pieces, or on either black or white, and it uses game.getMove as a source of moves. So what does that mean? Well, in game.java, there is a function getMove here, which returns a move. And it's going to call input.readLine, which looks like it's getting a potential move from the user. And so it then calls, process command on that line. So what's happening here? Well, the idea is that play is going to call the make move of whoever's turn it is. And so if we call make move on a human player, we're going to come here into this make move function. But then this make move function is going to turn around and say, okay, if I want to get a move from the terminal, then I need to come back to game and call get move. But get move not only processes a move, it's also able to handle any commands that get passed in. So for instance, if you are in the middle of the game and we call get move, if you're in the middle of a game and you call make move on a player, and then the player calls get move in the game, then perhaps even if the game tries to get a move from the player might try and enter a command like set or even clear and restart the game. And so we call process command here in order to handle that. If the user possibly inputs a command other than trying to make a move, we can handle that here as well. If the user does input a proper move, then what we'll do is we'll create a move object of that move and then make sure that that is actually a legal move. And if it is, then that move should get made inside our game. So again, there's sort of a dance going back and forth here where play is going to call the make move of whoever's turn it is if we are currently playing the game. And so that'll go to human player, but human player is going to turn right around and say, okay, well, game.java knows how to read a move in from the user, and it uses get move to do that. So that's what's going on here between game.java and the players. There's a few other functions to fill in this class, and once you've done that, then you should be all set up to play an actual game in your terminal. One note I want to make about this phase is how to test it. So in phase 1 with the board class, it was a little more practical to test using JUnit when you didn't have any commands written for the terminal yet. But when you are actually trying to test user input, JUnit becomes very, very kludgy, and it will probably end up being a big waste of your time if you try it. So I recommend you use the much better way of testing, which are the integration scripts that we have provided to you, as well as this script called test Loa, which you'll find in the 61B software repo. Now, these scripts, they're a lot like the ones from Project 0 and Project 1, where it will feed in whatever commands you give it into the program, and then expect the program to spit out the proper output. So, taking a look at init here, so the syntax for these tests is a bit different from the first two projects, which is why I do want to touch on it briefly. So, for every in and out script, the first two lines always designate which programs you want to start up. Now, in a very basic test, we just want to start our one program that we wrote and then give it some commands. So the syntax is we'll put this line here with these equals signs and then a number 1. And that means these commands will get fed into whatever the first program is that we wrote here, which is, well, just the Java loa.main that we wrote. So it will feed the command dump into it, and then hopefully it will check the out file to see whether or not it gave us the right output. And again, the syntax for that is you have to have a line that says program, and then the number of it, colon, and then after that, whatever else the output from the game is. So this command just very simply tests if we can dump it. So if I were to test this, I would type test Loa testing/init.in. And it passed. So it is very important that if you run test Loa by typing in test Loa and then the name of a test, you must run it from the project2 directory, not the testing directory. If you try to do that, it won't be able to find your program, and then it will tell you program crashed, error 1 for some unknown reason. And that will leave you confused. So run it from project2 directory. And also, you can always run make check to just run all of the scripts in the testing folder. Now, not every program or not every test you write will actually need both a .in and a .out file. And the reason for that is sometimes we don't actually care what the output of the program might be. We might actually care about what we're putting into it. So a good example of that is this test we provided, which is AI versus staff. So what this program does is actually lets you pit your AI, once you've written it, against the staff version of the project to see if you can actually beat the staff version. And so there are these special commands for in files that start with these percents, which you can read about if you just type testloa, and then it'll print out this long list of commands that you can use. So what these do is, well, we start a game and we set black to be an AI player, and we'll start the game. So this MB means it's going to wait for the user to, or it's going to wait for the AI in this game to give it a move. And it's going to give it a black move, saying black moved here. And then it will actually take that move and place it into our staff game. So this command means the staff game is waiting for a black move to be passed in from the other program. And then once it receives one, it will put that command into the game as if a human player inputted it. And then its own AI, the staff AI, will spit back another move, this time a white move. And so the script will pass that white move back over to our game with this command, which is waiting for a white move. And once it receives a white move, it's going to put it into the game as if a user inputted it, and then get a black move back, send it over to the other program, and this process will continue back and forth until the game reaches a conclusion, at which point a winner will be announced. And so we use %e to make sure that a winner was actually declared. Now, the reason that we only have a .in file instead of a .out file is because, well, we may not necessarily know or care who the winner is of the program, and also we may not care what each move actually is. Perhaps all we want to test is whether or not we can actually play a full game to completion between our program and the staff version. So in that case, when you don't care what the output actually is, you can use these commands to just specify, I'll take in any move, doesn't matter what it is, and pass it back and forth until the game announces a winner. Doesn't matter who it is. So that's how the testing script works. There's two ways to do it. Again, one using in and out pairs, and then one using these special commands that are provided in the test LOA script. All right, welcome to phase 3 of the project, your own artificial intelligence. So hopefully now your game.java is all set up to accept player commands, your board works properly, you've tested them both, and perhaps you've also gotten a chance to play a game against a friend in the terminal. Now it's time you made your own computer player, an unstoppable computer player, capable of beating any human that tries to stand against it, and perhaps even the staff version as well. Now, all of the code you'll be writing for this part of the project will be contained inside Machine Player here. Machine Player class is a type of player which, when its make move is called, well, it needs to return what move it wants to make based on analyzing the game in a whole series of ways. So the AI needs to be smart. But let's not worry about smartness yet. Let's worry about just trying to get it to make any move. So I would start in this section. Perhaps the first step would be just to get the machine to make a move. So instead of returning null here, let's have it return some dummy move, say h2 to f4. And we have to pass in our board. So now if I were to run the game against this AI, and I start up a new match for it here. Okay, so let's say I move B2 to B1 to D3. Okay, and now if I look at the board, we'll see that, yes, the AI did move this white piece from H2 to F4. So we actually got the computer to make a move, but that move isn't very exciting. It only works one time. So we need a way to actually check a bunch of moves and perhaps try different ones. So second step would be to get the machine to try different moves. So it would be nice if we had a way of getting the AI to iterate through a bunch of different possible moves and then maybe try one out, or maybe even analyze them to figure out which move is good or bad. Now, if you've been reading the skeleton carefully, you may have noticed that the board class actually implements iterable. So what does it mean to iterate over a board? Well, it's been given. It means that you can iterate over the possible moves at a particular board state. And we do this with the use of a move iterator object that has been provided for you, except for this inker function you need to fill in. So once your move iterator works, this will allow you to iterate over all the possible moves from a particular board state, and then perhaps make one or try it out and analyze it. So after you've gone through and written your move iterator, you'll be able to do something like this, where you can just loop over all of the possible moves at the current board state and, I don't know, maybe just return move. So here's a strategy that would just return the first possible move. You might try other strategies, like returning the second move or returning a random move. But we want to be intelligent. And so this next part of the project, part of this AI, is getting the machine to try good moves. So now it's important to actually come up with a metric for measuring how well a move will be for you. So I highly recommend at this point that you create some helper function like eval, which takes in a board state and it returns some evaluation of that board. And the higher the number you return, the better the move is. Okay. So now with this function, within here we can go ahead and try different strategies for looking at a particular board state and saying, will this move help me or not? And there's many things you could try in this case. For instance, one strategy you might try is, I don't know, the more pieces I have, the better. And you could try those moves. But that might not necessarily be the best strategy, right? Because the more pieces you have on the board in lines of action, the more you actually have to connect together in order to win. So maybe the more pieces you have might actually not benefit you as much as you might think. So in this function, you just want to compute different values for a particular board state. And then based on whatever value you return, I don't know, maybe in your make move, just return whichever one gives you the best value. Now, even the idea of looping over all the moves on the board and making the one that gives us the best evaluation isn't enough, because we're only looking one move ahead, and we're not taking into consideration what our opponent might do after we make that move. So, in fact, to make a truly intelligent AI, you're going to have to look moves ahead, several moves ahead, in fact, to figure out the best move you should take. So the next step is getting the machine to look ahead while trying moves. And this process could take a while. So in addition to looking ahead, you're going to need to look ahead efficiently, because it takes a lot of time. There's many different combinations of moves that could be made, and trying them all is going to take too long. Remember, your AI needs to find wins, but it also needs to find them within a certain time limit. So trying everything will be too much. Now, if you look at the data structures textbook, you'll find a great discussion on game trees, on how they work. And in addition, there's some great pseudocode that you should take a look at for coding your own minimax algorithm, we call it, to find the best move in a game tree. Now, as for being efficient, there are a few optimizations you should keep in mind. One of them is some moves will lead to the same board state, or some combinations of moves will lead to the same board state. And so if you ever reach that state again, maybe you don't want to have to do all that recalculating for that move. And to guide you along with that, notice that the board class does have an equals method and a hash code method, which do hint that you might want to fill them out in some way that will benefit you. Another optimization is called game tree pruning. So even as you are running your minimax algorithm on the game tree, there will be some moves that you know you don't need to look at. And so you can just stop calculating that part of the tree and try a different move instead. This is a very powerful optimization, and in fact, it's very hard to complete this project without pruning. So at the end of this video, I'll be doing a little explanation of game tree pruning and how that works. And once you've done that, you should have an unstoppable AI, which you can play against and perhaps try and trick your friends into beating as well. Thank you for watching, and good luck on the project. All right, now I'll be doing a demonstration of game tree pruning. And I'll be using the cutoff terminology because that is what's used in the data structures pseudocode for game trees, which I highly recommend, again, that you take a look at. And P.S., this was developed by Alex Kamko, a TA last semester. Thank you for this. You're awesome. So, in a game tree, every node in the tree represents a particular board state, or some combination of moves that got you to that state. And every link represents a possible move from one state to the next. So the root of the tree is always going to be the current board state. So, and it's going to be my turn. So I am an AI, say, and it's my turn now, and I'm looking at a particular board state. And I want to decide what move I should make. And in particular, I want to decide to make the best move I can so that it'll help me the best, or help me win. So we need to come up with some metric first to decide what makes a board state good or bad for me. And so once you've come up with some metric, we're going to use that metric to decide what move we should use. Now, at the very bottom of the tree here, these are a bunch of game states, and they have some particular evaluation. So we've taken this board state, run it through our evaluation function, and it returned us this particular number. It says how good or bad it is for us. And then we're going to run the game tree algorithm to decide which move to use. So, from this current board state, I have a choice of 3 possible moves. And let's say I make this one, B1 to D3. Now, it's going to be my opponent's turn at that point. And so my opponent is going to have a choice of these 3 possible moves. And let's say they choose this one, H2 to F4. Now it's my turn again. Now, at this point, we're going to stop the recursion because let's say we defined our tree to have a depth of 2. So we have recursed down twice, and then now it is my turn 2 moves ahead. And I'll actually need to decide what my next move will be at that point. So at this point, what's going to happen is, well, I want to choose the move from this board state that's going to maximize my score. So I'm going to look 1 move ahead to these next possible board states and decide which one will be best for me. So I'll start looking at this one that has a value of -4. So now, so far, the best I can do from what I've looked at is -4. Then I'll look at the next move and I'll see I could do a move that scores 11, which is better than -4. Now, do I need to keep looking at this point in this subtree? Yes, I do, right? Because I don't know what this is yet. It could be greater than 11. So I'll look, but it's not. So now I've determined that the best move I could do from this board state is 11. So that tells my opponent that if he were to make this move here, then I could play some move that has a score of 11. Now, my opponent wants to minimize my score. He wants me to do the worst that I possibly can. And so he's going to keep looking for each of his possible moves to see if one of the moves is such that no matter what I do, I can't do any better than what I already can, or what he's seen from a previous move. And let me explain that. So now we're going to look at, okay, maybe the opponent makes this move instead. Now I am here again, it's my turn, and I have a choice of these possible moves. So I look at this first one, and I see that I could make a move that is a score 19. So I'll say, yes, 19 is a good score. I want that. And now the question to you is, do I have to keep looking at these next moves? Go ahead and pause the video and think about it. And the answer is, no, we don't have to keep looking. Now, let's think about why. So we know that the opponent had the choice of these moves to begin with. And we know that if the opponent chose this move, the best score I could get is 11. Now, if the opponent were to choose this move, now we see that I have a move that has a score of 19, which means I will either pick 19 or some other score that's at least 19. But for any score that's 19 or larger, I know the opponent would never choose this move because that's already better for me than 11. So the opponent will stop looking down this tree and just say that it's never going to make this move because it already has a move that will be better than what I can do at this move. So it's going to move on. So it'll try this third move, and now it sees that I could get 14. Now, are we going to keep looking at this tree? No, for the same reason as before. 14 is already better than 11, so the opponent will never choose this move. So we bring that information back up, and now I know that if I were to make this move, the best that I could do is 11. So now let's say I try this move instead. So it's now my opponent's turn. The opponent, let's say, makes this move, and then now I'm here. Let's say I make this move, and this has a score of -6. Okay, this has -16, and this has 10. Okay, so the best I could do with this move is 10. Now the question is, am I going to keep looking at these two trees? Go ahead and pause the video and think about it. So, am I going to keep looking at my opponent's moves here? The answer is no, I don't need to. Now, the reason is similar to before, except now we're the ones making the intelligent pruning. So we know that if we were to choose this move, the opponent has the ability to choose this one such that the best I can do is 10. So if I were to make this move, then the best I can do is at most 10, because the opponent will either choose something that makes me, or that gets me a score of 10, or worse. But 10 is already less than the best I could do with this move. So I'm never going to choose this move because I know it could get me at most 10, which is worse than I can already do. So I'll just prune the tree at this point and stop looking at any of these moves. So that is the basics behind game tree pruning. The idea is you can quickly determine whether or not you will ever take a move, and if not, you can stop looking down part of the tree and save yourself a lot of time computing scores. So I hope this was helpful to you, and good luck in your game tree pruning.